Myself Prema Sarvamanit. My topic is crystal field theory, crystal field splitting, calculation and comparison of CFS in octahedral and tetrahedral complexes. First, we know that or crystal field theory. We will discuss about crystal field theory, crystal field splitting, CFSE calculation, comparison of octahedral and tetrahedral complexes. First of all, we discussed about drawbacks of VBT because VBT drawbacks are the postulates of CFT. Valency bond theory explains bonding using hybridization. It is useful for understanding structure of coordination compounds, but it has several limitations. In VBT, cannot explain the color of coordination compound. Many coordination compounds are colored. VBT doesn't explain why compounds absorb certain wavelengths of light, but CFTs explain color better than VBT. Second drawbacks of VBTs cannot explain magnetic property clearly for coordination compound. VBT tells whether a complex is high spin or low spin, but it does not clearly explain the electron pair or remain unpaired. Magnetic behavior is not fully justified in the VBT. The third limitations of VBT is no concept of d orbital splitting. In free metal ion, d orbitals are equal in energy. VBT does not explain splitting of d orbitals in presence of ligands. It does not explain energy difference. The fourth limitations of VBTs cannot explain stability of complexes. VBT does not explain the why some complexes are more stable. No concept like crystal field stabilization energy or CFSE. The fifth limitations of VBT is no explanation of spectra. Electronic spectra of complexes are not explained. Absorption band or transition are not described by VBT. Only qualitative theory will explain the VBT. VBT gives only basic understanding. No mathematical or qualitative explanation cannot calculate exact energies. VBT explains hybridization and geometry but fails to explain color, magnetism, spectra and stability. Advanced theories like crystal field theory are more complete. So we let come to the point CFT or crystal field theory. The crystal field theory was proposed by Hans Bethe in 1929. Explains bonding in coordination compound based on the electrostatic attraction between metal ion and ligand, mainly used for the transition metal complexes. Basic idea of crystal field theory. Metal ion is positively charged, ligand are negatively charged or have a lone pair. Attraction occur between them, repulsion affect d orbital energies. Some assumption of CFT. Ligands are treated as a point charges. Bonding in purely ionic, electrostatic. No covalent interaction considered. Free metal ion has a d generated from d orbitals. So, we have discussed about postulates of CFT. The main postulate of CFT is nature of bonding. Metal ligand bond is purely electrostatic. Ligand are treated as negative ion or natural molecules. No sharing of electron is considered. Effect on d orbitals. In free metal ion, all 5 d orbitals have a same energy or degenerated. When ligands approach, repulsion occurs between d electrons of metal. Splitting in octahedral complexes. In octahedral field, d orbitals split into two groups, T2g and Eg. T2g have a lower energy and Eg have a higher energy. T2g orbitals have dxy, dyz and dxz. Eg orbitals have dxz, dz square, dx square minus y square. Energy difference is called crystal field splitting energy. Splitting in tetrahedral complexes. In tetrahedral field, splitting is reversed to octahedral. E have a lower energy and T2 have a higher energy. Energy gap is called delta T. Delta T is smaller than delta O. Smaller electron fills orbital according to Aufbau principle, Hand's rule, Pauli exclusion principle. Complex can be high spin and low spin depending on the ligand strength. spectrochemical series. Ligands are arranged based on the field strength. Field strength. Strong field ligands have a large splitting. Weak field ligands have a small splitting. So, what are the 5 d orbitals? We have know that dyz, dxy, dxz, dz square, dx square minus y square. In free ions, all have a equal energy. These are the shapes of all 5 d orbitals. So, what is crystal field splitting? When ligands approaches metal ion, the orbitals split into a different energy level because of repulsion between two electrons. So, we discussed about octahedral complexes. 6 ligands surrounded by the metal ion. Ligands approach along the x, y, z axis. Example FeH2O6. FeH2O6. 6 is the octahedral complexes. Splitting in octahedral field. Two groups are formed, Eg and T2G. So, we know that Eg have a higher energy, T2G have a lower energy. Energy gap between delta O. So, field splitting on d orbitals or orbitals. In octahedral, what type of orbitals have split? Free metal ion, spherical charges field, 6 localized point charges orbitals field. So, the difference between barycenter to Eg and barycenter to T2G. The difference is barycenter to T2G is 0.4 and barycenter to Eg is 0.6. This type of splitting occurs in the d orbitals. This is the energy diagram of octahedral. T2G stabilized by 0.4 and Eg destabilized by plus 0.4. Total energy remains balanced. What are CFSE? CFSE expounded as crystal field stabilization energy. Energy gained due to splitting depends on number of electrons in T2G and Eg. CFSE formula in octahedral. CFSE formula, we know that CFSE crystal field splitting energy. One example for CFSE, D5 configuration. So D orbitals have a 5 configuration in high spin. T2G have a 3 electrons and Eg have a 2 electrons. CFSE in number of T2G plus number of Eg. Number of T2G electrons is 3 into minus 0.4 plus 2 into plus 0.6. The calculation is or CFSE is equal to 0. Tetrahedral complexes. We know that a tetrahedral means 4 ligands surrounded by a metal ion. Ligands approach between the axis. In octahedral, ligands approaches along the axis. Z and Cl4 is the example of tetrahedral complexes. Splitting in tetrahedral field. Two groups formed, E and T2. Lower energy is E and higher energy is T2G. Tetrahedral is directly opposite to octahedral complexes. This is the field splitting in tetrahedral complexes. Difference between tetrahedral. T is smaller than delta T is smaller than delta O. Delta T is equal to 4 by 9 delta O. Therefore, splitting is weaker. CFC formula in tetrahedral. CFC formula is also reversible to octahedral complexes. CFC is equal to number of T2 into 0.6 plus 0.4. Comparison of octahedral versus tetrahedral. Octahedral splitting is larger, but tetrahedral splitting is smaller. Delta O is smaller than delta T. Octahedral more stable generally. This is the diagram. Explain the comparison of octahedral and tetrahedral in simply explain. High spin and low spin. Delta O is small or high spin. Large is low spin. Tetrahedral mostly high spin complexes. Why CFSC is important? Explain stability of complexes, explain color, explain magnetic properties. CFT explains splitting of d orbitals. Octahedral and tetrahedral have a different splitting. CFSC can be calculated using simple formulas, useful in understanding properties of complexes. So, what are the questions arise in about crystal field theory? What is crystal field theory? What is crystal field splitting? Define CFSC or expand CFSC. Give the formula of CFSC calculating on octahedral complexes. Same as give the formula of CFSC calculating on tetrahedral complexes. Comparison on octahedral and tetrahedral complexes. Thank you to all.